Greetings YouTubers. My name is PhD Tony and today I would like to present the first in what I hope to be a series of presentations on climate science. In this first episode I'll present the theory behind the so-called greenhouse effect and the observational validation of that theory. I will then present the evidence that carbon dioxide is a greenhouse gas and that the recent rise in global mean surface temperatures is the result of a greenhouse-driven process. The study of climate physics began in earnest with the work of Joseph Fourier. Fourier was a French mathematician of the early 19th century who developed much of the analytical techniques still used in the modelling of heat transport processes. In 1827, Fourier asked an apparently simple but ultimately profound question. Based solely on the energy Earth receives from the Sun, what should the mean surface temperature of Earth be? Rather than follow the working of Fourier, I will present the more modern analysis of this problem, which agrees with Fourier's original results. We begin by considering the energy balance of the Earth. Conservation of energy dictates that any energy Earth receives from the Sun must be re-radiated. The equation presented here represents the energy received from the Earth by the Sun. In this equation, S is solar energy flux at Earth's radius from the Sun, A is albedo, the reflectivity of the planet, and R is planetary radius. For the present-day Earth, A is approximately 0.3 and S is approximately 1373 watts per square metre. The formula for the energy radiated by the Earth takes a more complex form derived from the principles of statistical mechanics and the radiation from a black body. This is the Stefan-Boltzmann equation. In this equation, sigma, the little circular symbol, is the Stefan-Boltzmann constant, Te is the effective emission temperature of the planet, and the 4 pi r squared term is the surface area of a sphere of radius r. Since we know S, A, and sigma, we can determine that Te, the effective emission temperature, is 255 Kelvin, which is minus 18 degrees centigrade or 0 degrees Fahrenheit. Earth's mean surface temperature is observed to be 288 Kelvin, which is 15 degrees centigrade or 59 degrees Fahrenheit. There is thus a significant discrepancy between the observed mean surface temperature and the calculated effective emission temperature. So is our theory just wrong? Satellite observations of Earth's radiation budget suggest that the theory is in fact correct, and the Earth does radiate infrared consistent with an effective emission temperature of 255 Kelvin. We can further validate our theory by considering the case of other planets. Venus, for example, is observed to have an effective emission temperature of 178 Kelvin, but a mean surface temperature of a staggering 740 Kelvin, showing that surface temperature and effective emission temperature can be very, very different. The initial radiative transfer modelling of the Venusian atmosphere was actually undertaken by Carl Sagan and later validated by the Venera satellite probes. All of which begs the question, why is this happening? To answer this question, we're going to consider the case of a satellite high above Earth's surface outside of the atmosphere, as illustrated in this schematic diagram, which I hasten to point out is not to scale. Earth's atmosphere is effectively transparent to radiation in the visible light portion of the electromagnetic spectrum, but the same is not true in the infrared portion of the electromagnetic spectrum. In that portion, a satellite outside Earth's atmosphere can only see a limited depth into the atmosphere. This depth is defined as 1 optical thickness. A satellite outside of Earth's atmosphere will only be able to see as far as altitude HE. This is called Earth's effective emission altitude. This is the altitude inside Earth's atmosphere from which a photon of infrared radiation can expect to be emitted directly to space without being reabsorbed by any gases inside the atmosphere. For present-day Earth, the effective emission height is approximately 6.5 kilometers, still well within the troposphere. All of this may seem interesting, but rather abstract and unrelated to the problem that we're considering. But in fact, we have all the information we need to explain how the greenhouse effect works. As the atmosphere becomes more opaque to infrared radiation, a satellite outside the atmosphere cannot see as deep into Earth's atmosphere. In other words, the effective emission height, HE, rises. It gets higher away from the surface. But since in the troposphere temperature increases as altitude decreases, and the temperature of HE is fixed, as you move HE higher, the surface temperature must rise. The next question to ask is which gases in Earth's atmosphere actually absorb infrared radiation? And this is where we turn to spectrographers, who have compiled an exhaustive list of gases that are present in Earth's atmosphere and their absorption and re-emission properties in the infrared spectrum. These results have been compiled in the HitRAN database, which is regularly updated and validated against observational evidence. This figure shows satellite observations of the intensity of infrared radiative emission from the top of Earth's atmosphere as a function of wave number. The red curve is what might be expected if the Earth were emitting infrared radiation consistent with its mean surface temperature. The blue lines represent the actual observations. By inspection, we note that the blue curve has a lower amplitude than the red curve, consistent with a lower emission temperature, and also that its maximum emission is offset slightly to the right, again consistent with a lower emission temperature. We also note that the observations lack the smooth profile that would be suggested by our theoretical results. This is because of the presence of a very large number of jagged irregularities. These irregularities are the results of the absorption of infrared radiation by molecules of greenhouse gases. The left-hand panel of this figure shows the model results for a combination of the absorption and emission spectra determined by the HitRAN analysis and a radiative transfer model. The black curve shows the model results for all greenhouse gases. The different colored curves show cases where individual greenhouse gases are excluded from the model results. The right-hand panel shows the infrared absorption characteristics for each of the greenhouse gases in turn. We can see from the black curve in the left-hand panel that the agreement between our observations and our model predictions is extremely good. We now turn our attention to the pattern of mean surface temperature over the past 140 years and the corresponding pattern of solar irradiance. These are illustrated in the red and yellow curves respectively. As can be immediately discerned, there has been a significant increase in mean surface temperature over this period. Accurate observations of atmospheric carbon dioxide concentration have only been possible since the late 1950s. However, since that time, a steady and significant increase in carbon dioxide levels has been observed. This raises the possibility that a greenhouse warming might be induced. One strand of evidence we can appeal to determine whether or not the observed trend in warming is due to greenhouse forcing is the trend in nighttime temperatures. As the atmosphere becomes more opaque to infrared, we expect heat to escape the Earth's surface more slowly. As a result, we expect nighttime temperatures to rise more rapidly than daytime temperatures, creating what is called a diurnal asymmetry in warming. This figure shows observational results for the North American region. The middle panel shows the trend in daytime maximum temperature or maximum daytime temperature. The bottom panel shows the trend in daily minimum temperature or minimum nighttime temperature, and the top panel shows the difference between the two, which reduces as a function of time, showing that indeed nighttime temperature is rising more rapidly than daytime temperature. A second strand of evidence we can use to determine whether or not the current warming trend is due to greenhouse forcing is the trend in stratospheric temperature. For complex reasons involving the rate of infrared emission, we expect the stratosphere to cool as the troposphere warms. And the observational evidence from satellite measurements suggests that this is exactly what is occurring, so that the warming trend again is exactly consistent with what is expected from the theory of radiative transfer modelling and greenhouse gas forcing. So that brings us to the end of this episode. What I hope that I've demonstrated in this presentation is the existence of the greenhouse effect and its significance in determining planetary surface temperature. I also hope that I've demonstrated that carbon dioxide is a greenhouse gas and that atmospheric carbon dioxide concentrations have risen since the 1960s. Similarly, global mean surface temperature has risen since the 1960s, and the pattern of that warming is consistent with greenhouse forcing. In the next episode, I will be examining the source of the carbon dioxide being added to the atmosphere and the role of water vapour in the planetary climate system. If you have any questions, please feel free to contact me in the comment section below, and thank you very much for watching.